Hi, my name is Alina, and today I present our work on accurate vision-based manipulation through contact reasoning. So, what is hard about vision-based robotic manipulation? The first challenge that we face is that manipulation is inherently contact-driven. Take, for example, the planar pushing task shown on the right, which we use to demonstrate our method on. If we look at the video, it becomes clear that for pushing the object towards the red goalpost, you don't only have to plan how the robot pushes the object, but also where it makes contact with it. Unfortunately, optimizing both contact locations and robot motions jointly is both difficult and computationally expensive due to the large numbers of combinations. A second challenge is that the state information that we can get from visual input is often inaccurate and noisy, and sometimes even incomplete. Approaches that rely on visual input therefore often achieve a much lower accuracy than approaches that assume access to the full state information. In our work, we address both of these challenges. First, we improve planning efficiency by separating contact and motion optimization. This allows us to focus expensive computations on few promising contact locations. And second, by combining neural networks for perception with analytical models for optimizing actions, we can improve significantly on the accuracy reached by previous vision-based approaches on this task. Now let me walk you through our approach step by step. We start each sequence by using a neural network to extract a representation of the object shape from the RGBD input. This representation contains points on the object outline, which you can see visualized here, together with their coordinates and estimated normals. Since we assume that the object is rigid, we only have to compute this step once in the beginning of interaction. The second step is state estimation. We again use a neural network to extract the current position and orientation of the object from the visual input. This pose information is then fed into an extended Kalman filter, together with the last push that the robot performed. This filtering step does not only improve the robustness of the estimated pose against occlusions or other noise, but it also allows us to estimate properties like the center of mass of the object that we could not observe from single images directly. Once we know where the object is and where we would like it to go, we now search for contact points that are suitable for pushing the object closer towards that goal. For this, we annotate the whole object outline with what we call affordances. The affordances of a point are simply a representation of all the object motions that we can achieve by pushing there. We compute the affordances by predicting the outcome of a small set of representative pushes at each point. Since we have to do this prediction step for every point on the object outline, we use a very cheap and approximate model for the prediction. In our experiments, we evaluated two different models for predicting affordances. One is an approximate analytical model of pushing, and the other one is a learned neural network. Once we have the affordances, we can score each point by how well the desired object motion coincides with the motions that this point affords. You see the scores visualized here, where lighter color means a higher score. Using the scores from the affordances, we can now sample a small set of candidate contact points that we want to evaluate further. For these few points, we can now afford to use a more exact, but also more costly analytical model to optimize the actions that we would take at each point. Finally, we select the best contact point and action pair and execute the push. This process is then repeated until the object comes within 75 mm and 5 degrees of the target pose, or until a maximum number of allowed steps was taken. Let's now take a closer look at the results. In the first experiment, we wanted to see how useful the affordance models really are for selecting contact points. To test this, we evaluated how many contact points we need to sample with different methods to reliably solve the pushing task. Here we compared our method in red to two baselines in gray. The first baseline just samples contact points uniformly from the complete object outline, whereas the second one uses a geometric heuristic to reduce the sampling space to the more useful regions of the object. As you can see, when we use an affordance model, be it an analytical or a learned one, we can already reach a success rate of close to 100% when we sample only one contact point per push. In comparison, with the uniform sampling, we have to sample more than 10 points per push to arrive at the same result. But our method does not only make planning more efficient because we have to sample and evaluate fewer contact points. The right plot shows the number of steps that each method took in successful runs to reach the goal. As you can see, when we use the affordance models, we also have to perform significantly fewer pushes. This is because the affordance models propose contact points that afford more optimal pushing actions than contact points that have been selected randomly. And finally, you can also see that there is not a large difference between using an approximate analytical or a learned model to predict the affordances. So does that mean that both of the affordance models make accurate predictions of the pushing dynamics? To answer this question, we performed an experiment where we replaced the exact analytical model that we used for action optimization in the previous experiment with the more approximate model that we use for predicting affordances. So here you can see the original method with the exact action optimization in red, and the variant where we use the affordance model for action optimization in brown. We again look at how many steps each of the methods took to reach the goal. And we can see that there is only a small difference between using the exact analytical or the approximate analytical model for action optimization. Things, however, look different if we consider the learned affordance model. Here you can see that using the learned affordance model significantly increases the number of pushes that we have to perform. This shows that while the learned affordance model is accurate enough for predicting good contact locations, we can still gain a lot in terms of accuracy when we rely on an analytical model for optimizing the actions. In the final experiment, we compared our method to PushNet. Similar to our method, PushNet also relies on visual input and is also able to estimate the position of the center of mass of the objects over time. However, in contrast to our method, PushNet completely relies on learned components for both state estimation and predicting the outcome of actions. The approach also does not reason about contact locations explicitly, but simply samples and evaluates a large number of different pushes. We compare the methods in simulated experiments with increasingly small target area sizes. In this experiment, the center of mass of the object is also placed at a random location in each trial. As you can see, both methods perform well on the large target area, but as the target region gets smaller, our method maintains a much higher success rate. We also again look at the number of steps that the methods took to reach the goal, and we can see that our method also reliably uses fewer steps. We believe that this difference in accuracy is mainly caused by the larger amount of prior structure that we integrated in our approach. This prior structure, of course, contains the extended Kalman filter and the analytical model for optimizing actions, but also the insight that we separated contact and action optimization. To summarize, our experiment showed that by explicitly reasoning over contact locations in manipulation, we can not only improve planning efficiency, but also the quality of the planned motions. We have also seen that for proposing meaningful contact locations, an approximate, maybe even learned model is sufficient. However, when it comes to optimizing the actions taken at each contact point, we can reach a higher accuracy by relying on an analytical model of the dynamics. Thanks for watching my talk. If you're interested in more details, or if you have any questions, please don't hesitate to contact me. I'm looking forward to meeting you.